So today we're going to talk about how to do a special kind of significance test for paired means. Paired means. So on Friday we talked about two sample t-tests, and we today are going to do paired t-tests. Now the thing is that they look a little similar, but here's the difference. So what is a paired t-test? When I say something about paired data, do you think about anything that you've learned in this class at all? Paired data. No. Paired data. Anybody remember back in the unit where we talked about how to do samples and surveys and experiments? How sometimes we might have something called a matched pairs design. Does that sound familiar at all? Maybe? Okay. So matched pairs design. Remember we talked about this problem where we were going to try to see if talking on a Bluetooth telephone in your car, if that was distracting you or not. And we did a simulator where one time you would go through the simulator with the distraction. One time you would go through the simulator without the distraction. And we wanted to see if there was a difference. That was a matched pairs design. So matched pairs, if you remember, is anytime one person is getting both treatments and we're seeing if they have a reaction to the treatment, or we're pairing them with someone who's just like them in every way possible. So a paired t-test is a significance test over a matched pairs experiment to see if the treatment makes a significant difference. It is a significance test over a matched pairs experiment to see if the treatment makes a significant difference. So we want to see, does this driving while you are distracted, does that really make a significant difference or not? We want to see if this drug makes a significant difference. So we let somebody do a trial with the placebo and then with the drug, and we compare them to themselves. That's the matched pairs part. And so it's basically a matched pairs design, and we're trying to see if the difference is made. So how do you tell if a problem is a paired t-test or a two sample t-test from what we did on Friday? So basically what you need to do is identify if more than one treatment is applied to each individual. If more than one treatment is applied to each individual, if each individual gets access to both treatments, you have a paired t-test. If each individual is only getting one treatment, and you're looking at does this group act different than this group, then you're doing two. You have two separate groups, okay? So it's basically like, are we pairing and each is getting treatment, or are we grouping and each group gets a single treatment and we're comparing those, okay? That's basically how you're going to tell. Now, how does this affect the way that the problem is completed? So, if we have paired data, we do a one mean t-test on the difference in observation. So at that point, if we're pairing up to see if there's a difference, we're going to look at the difference, and we're going to just do the significance test on the actual difference itself. Was there an actual difference, a significant difference, or not? So if we have paired data, we're actually going to use our one mean t-test on the difference. We won't use the original, two different treatments. We won't use all the original data. You'll see what I mean when we get to our example in just a minute. But first, what we're going to do is we're going to look at a few situations, and we're going to try to make sure we understand the difference between, would I use a two t-test, or would I use the paired t-test? So let's look at a couple of these examples. Luke's Taco Shop. In each of the following settings, we're going to decide whether or not it's a two sample or whether it would be a paired. So number A. Let's go with it. Sure. Luke's Taco Shop is considering a switch to new tortillas that supposedly have a larger diameter. To test this claim, Luke takes a random sample of 50 of the old tortillas and 50 of the new tortillas and records the diameter of each. Do I have pairing here, or am I pairing something? Am I getting two treatments, or do I have just two different groups that are getting something done?
Two different groups.
Yeah, I've got two different groups. I've got the old tortillas versus the new tortillas. I'm going to look at the average diameter of the old tortillas versus the average diameter of the new tortillas and see if there's a difference. So this is two clear groups, and so I would use a two mean t-test like we did on Friday. So this is two groups, the old versus new. And so we would use a two mean t-test in this problem. I'm just comparing if the old and the new are different diameters. So that would be a two mean t-test. All right, B. Luke's Taco Shop wants to be sure that the new tortilla tastes better than the old tortillas. Luke selects a random sample of 20 regular customers. Each customer is asked to try both tortillas and then record the taste score for each. The order in which the customers try the two tortillas is randomized. Is this a two mean or is this a paired mean? Paired. I am pairing each customer with themselves. They get both of the tortillas to try, and we're going to pair their own particular taste buds with themselves. So this would be a paired t-test. This would be a paired t-test. Now that's going to work just like a one mean t-test, but it would be a paired t-test. All right, Luke's Taco Shop is not sure whether to cook the tortillas in the oven or on the grill. The chef wants tortillas to cook as quickly as possible. Luke sets up an experiment, taking a batch of 50 tortillas and randomly assigning half of them to get cooked one time in the oven and half of them to be cooked one at a time on the grill. The time it takes until ready to serve is recorded for each tortilla. Difference, or two different, is that what you're saying? Two different, okay. Am I pairing anything? No. Is each tortilla getting both treatments? No, then they would all be overcooked. If I cook them in the oven and the grill, I would have lots of overly cooked tortillas. That would be stupid. So basically what we're doing here, guys, is we're looking at the time it takes to cook in the oven versus the time it takes to cook on the grill, and we're looking at the two big groups. So this would be a two mean t-test. So we have two groups. We have grill versus oven, and so this would be a two mean t-test. And so we would complete that like we completed it on Friday. Cool? Cool. We're having a good time, aren't we? Guess what, you guys? We just have one problem and we're done. Isn't that exciting? All right, let's do it then. Caffeine. We're going to talk about caffeine. Any of you guys caffeine dependent? Not really. Okay, good. Don't get hooked on caffeine. It's bad for you. Or is it? We're about to find out. Researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, and other substances with caffeine for the duration of the experiment. During one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo capsules. The order in which the subjects took caffeine and the placebo was randomized. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know if being deprived of caffeine would lead to an increase in depression. The table contains data on the subject's scores on a depression test. Higher scores show more symptoms of depression. Carry out a test to investigate the researcher's claim. So first of all, I want to make sure you guys understand the table. So if you look at the first column, that's just the number. It's just giving everybody a number, the 11 volunteers. Depression with caffeine. This is their depression score when they get their normal caffeine intake. Who is the most depressed even with their caffeine? Subject number 10. Now, subject number 10 is the most depressed even with their caffeine. Who is the least depressed with their caffeine? 7 and 8 show no signs of depression even with their caffeine. So good for them. Yay for them. Now look at the placebo. Notice the scores have gone up for pretty much everybody. Who is the most depressed when you take away their caffeine?
6.
Oh boy, get that person some help. Who is the least depressed when you take away their caffeine? 11. Oh, look at 11. 11 seems to be an anomaly. What happened to 11? They actually got less depressed when we took away their caffeine. So they should probably stop caffeine. Now, the final column is the difference. We're taking the placebo score and subtracting the caffeine score. Now, if caffeine lowers depression, so my caffeine score should be lower, if that's true, then I should be expecting to see positive numbers here, right? So, and for most of them, I do see that, and the only person that's different is number 11. So the way that this is going to work is, first of all, do we have paired data or do we have two different samples? Yeah, we have paired data. We're pairing each person with themselves, their own depression score with themselves. And obviously we can see if there's a difference, there's a column for the difference. So the way that this works, you guys, is we're going to do a one mean t-test on the difference. And that data right there is the only data that matters. I don't have to worry about anything else. I don't care about the shape of any of the distributions. I don't care about the sample size for the individual data here. The only thing I care about is the data that is given to me right there in that difference column. That's the only data that I'm going to do a test on. Cool? Let's do it. All right, we're going to do a state plan do conclude on the difference. There are a few teeny tiny little things that are different here because of the fact that we're doing a paired t-test and that this is an experiment, not just a survey or a observational study. So we'll talk about those as we go. But we're doing a state plan do conclude. Let's go. State. We will test at alpha equals, what does alpha equal? 0.05. All right, alpha equals 0.05. Now, here's the first difference. We are testing the mean difference, so it's mu sub d. Now, if caffeine makes no difference in your depression score, then what should the mean difference equal? 0. Oh, by the way, this is the null hypothesis. I should have wrote that down. So the null hypothesis here is that the mean difference is 0, that there's no difference in your depression, whether you're on your caffeine or you're not. Now, the alternative would be that the mean difference is, it's actually not equal, because greater than 0. Because remember, we're testing whether or not caffeine helps your depression. So your caffeine score should be lower, because lower depression score. Caffeine score should be lower than the placebo score, and we're doing placebo minus caffeine, so we should be getting positive numbers. We're going to define here mu sub d equals the true mean difference in depression score. And this is where we'll notate we're doing placebo minus caffeine. And so again, that's why we're looking for positive numbers to see if the caffeine depression score is lower than the placebo depression score. Okay, what's next? Plan. Random. Now, these 11 people volunteered to be a part of the study. So I don't have a simple random sample of 11 people. But what do I have in the experiment that was randomized? Yeah, the order of the treatments, right? So I can say here for random, the order of treatment was random. Okay, so as long as I have some randomization going on, then that works. All right, now here's another one that's a little different because of the fact that we're doing an experiment, the 10% condition. If you guys look at the sideboard over there and remember why we check the 10% condition, it is to ensure we have independent observations. It's to ensure we have independent observations. So what I need to make sure of here is, do you think that each subject would have an independent reaction to the depression from the other subjects? Yeah, everybody's caffeine dependence and depression is independent of everyone else's. So we can just notate here that we have independent subjects. The whole reason we check the 10% condition is to make sure we have independent observations, and our subjects are all independent and they're all reacting independently. So we have that under control. All right, normal. Again, we are looking at the difference, the mean difference. So, do we know what the shape is of the mean difference population? That would be a no. Do we have more than 30 mean differences? That would be a no. So guess what? Box plot on the mean differences. Woohoo! Box plot on a Monday morning. Isn't that great? Who's excited? I am so excited. All right, you guys, so here's the deal. Your calculator probably still has a lot of data in it from Friday, and you had like parallel box plots turned on, and you had all kinds of stuff going on your calculator. So if it were me, I would probably clear my calculator just to kind of reset everything so that I don't have weird errors showing up or whatever. Do you guys remember how to clear your calculator? Second plus 712. Second plus 712. I would go ahead and clear that calculator just because, again, you don't want to have weird box plot things showing up and all that kind of stuff. That kind of resets your box plots and everything. All right, so data. I need to put in the mean difference data. So where do I go to put data in? Stat edit. Everybody go to stat edit. And you are only putting in the mean difference column. That's the only column that matters, that far right column. Nothing else matters. So you're just plugging in those mean difference scores in the depression. In L1. Yeah, in L1. Yep. Stat edit, you're going to L1, and you're plugging in the mean difference of those depression scores. On the -1, the very last one, please make sure you use the -1, not a -1. That will give you an error if you don't do that correctly. Okay. Who remembers how to make a box plot? Second y equals. Second y equals. Hit enter on plot 1. Hit enter on. You'll go down to the type and right arrow over to the box plot with outliers. That's the fourth graph. And once you select that one, you can hit graph, zoom, 9. And you'll see your box plot of your differences. And how do you find out what numbers those are?
Trace.
Hit trace. You can go left and right. And we're going to sketch the graph. Whee! Wasn't that fun? Why not? Oh, but poor box plots, they get no love.
What do we click after on?
So you turn on the box plot, and then you go down to type, and make sure that it has the fourth box or the fourth graph, which is the box plot with the outliers, and then graph, zoom 9. Yep, and then if you hit trace, you can go left and right and see the box plot numbers, and you can then sketch your box plot. Okay, and what do we need to notate underneath this normal condition here by our box plot? What do we need to write down here? No outliers. Okay, what else? No strong skewness. So, what applies? So not central limit theorem. This is not the central limit theorem. But I can just say T procedures apply. Basically meaning I can use the T distribution, which is normal, because this was normal. So basically I can say the T procedures will work, the T procedures will apply here because of the fact that I had no outliers and no strong skewness. Cool? All right, so big differences here in the state is that we're using the mean difference, mu sub d. We're making sure that we are saying what order we're doing the subtraction in or the difference. Random with an experiment, as long as you randomize something in the experiment, you're good. 10%, make sure you're talking about independent observations. And then we're only checking the normal condition for the differences. We don't have to look at the other data. All right, what's next? Do. Let's do it. For do, we're going to use a paired t-test. The good thing is that it works just like a one mean t-test, which you guys have already used before. In your calculator, that's under stat test number 2, and it just says t-test. Stat test and number 2, and it just says t-test. Now, the first question it's asking you is, do you have data or do you have stats? We have data. We put that data into L1. We put the mean differences into L1. All right, the next thing it's asking you is mu sub 0. This is your claimed value of your hypothesis. What value did we use?
0.
A 0. We're trying to see whether or not our mean difference is 0 versus is it greater than 0. All right, our list is in L1. Our frequency is 1. We can leave that. And then our true mean difference, we're thinking is greater than the claimed mean of 0. So we would select that third one on the far right. And then you can calculate or draw your choice. Yes. Let's see. All right, you guys, what did you get for your t-test statistic?
3.53.
3.53. And next line?
P-value is 0.0027.
P-value 0.0027. 27. Okay, perfect. Okay? And because this is a mean, we need to write down our degrees of freedom. Degrees of freedom. How many degrees of freedom do we have?
10.
How'd you get 10?
Subtract 10. 1.
Yeah, 11 minus 1 is 10. So my degrees of freedom is 10. Perfect. What are we going to do now? Conclude. It's time to conclude. P-value equals 0.0027. How does that relate to the alpha in this problem?
It's
That is less than the alpha of 0.05. And if our p-value is lower than alpha, we are going to reject the null hypothesis. If we are rejecting the null hypothesis, do we or do we not have convincing evidence? There is convincing evidence that the mean difference, that mu sub d, the mean difference is greater than 0. That's our alternative. That the mean difference is greater than 0. So let's just check in with what that actually means in the context of this problem. Does that mean that caffeine is lowering these people's depression? It would appear so. It would appear that caffeine is affecting their depression because it is causing their depression score to be lower and therefore us having a difference greater than 0. We have statistical evidence showing that we have a difference greater than 0, which basically means that the caffeine is helping with their depression. Questions, comments, concerns? Cool.